The next part I'm going to talk about is the software and the software systems. In general, what is software engineering and what sorts of projects are there in development of software? Obviously, when we consider what the software itself is, we get the more general definition, like that the software is just something that includes the computer program, which has use procedures. We have set of rules, documentation, and the data the system is using. So basically, what this IEEE definition says is that the software is more or less just computer program with the source code, which more or less is just a collection of actions or commands which fulfills some procedure, and the package includes documentation which helps the people to use the software, and also that there's data involved, the things the software uses to function correctly. So, this is a rather generic definition, and it's not really that helpful, because if we consider all the other actual projects and things that are software, we come up with a huge list of different stuff like here. For example, software systems, operating systems, hardware interfaces are really complicated pieces of hardware when compared against things like media players or internet applets or games and stuff like that. Actually, I'm not saying that games or media player software are simple to do or easy to create. All software systems have hundreds and thousands of different components and parts, which all have to be developed. For example, the space shuttle has something like a million different sorts of components which they are built from, and it's not very hard to imagine that there's at least the same amount of different source code components in large operating system. So in one way, software projects and software products can be as complicated things of engineering as space shuttle or anything related to space and rocket industry. So in itself, considering that we have software everywhere, you probably can't even use your toaster without having to work with some embedded system, or you definitely can't use your microwave oven without having used some embedded system, because probably the timer in your microwave oven is actually a piece of software. So, adding to all these types of software projects together, it's actually really interesting to see how much different things we do. And, well, there's many similarities here, but also differences. And if we say that we are developing software, we are just saying basically that we are doing something with computer. What the part that's same with all these different projects is the requirements. The requirements define what you are building and how you should be building it, and this is the thing that actually defines the software. So what's the response time? Does it have to function immediately, or can it wait? What's the real-time requirement? We can't wait for the airbag in an accident to load its driver and install update, and then the Java runtime environment starts to do its thing and fail, for example. Data management requirements, usability requirements. For example, with a complicated industry control system, you can expect that the company also teaches their employees how to use the software. Whereas if you have video game, which you have to have courses for people to be able to play it, you probably end up with a problem in that behalf. Also, mission criticality, meaning that if you have intensive care system which gives drug overdose to your patient, or customer register system of small company, if they fail, of course these are both critical and bad situations. In intensive care system, the patient dies. On the small company system, the customer register is lost, both which are catastrophic failures, but of course in different scales. On the other hand, the scope and mission criticality are also two different things. For example, if you have a customer register for a small local company, it's not the end of the world if you lose all your customer data. But if you have international huge company and you lose or the data of your customers is stolen, that's pretty close to catastrophe. Like, for example, when Sony decided to lose all their customer data or their customer credit card information to some hackers which just found out that the Sony PlayStation 3 had really laughable security system for handling the customer information. Today we are talking about these software production problems simply because software is everywhere. And not only is it everywhere, we are dependent on it. Also, since the software applications are becoming larger and more complex, I mean in the 60s, 70s, even 80s, the computer software was something that just functioned in one computer or server system somewhere, and if it broke down, you just had one broken computer. And the software could be fixed, and then the system would be running again. And that would affect only that one office, or one person, or one factory. But since we are more connected to everywhere, it means that we are more likely to run into problems with the where problem in software replicates in many places, and because the systems are more complicated or complex, there's more difficult problems everywhere, and since we are expecting that things go forward, that we have more features and more functionality, it also means that the software systems, software applications are harder and harder to develop. Also adding into this problem is that we are doing most of our development work in subcontracting, or use external components, or simply we have several offices which one is in, for example, in India, one is in Finland, and one is in Northern America, so that we can have continuous development throughout the 24-hour cycle. It means that not only are we building more complicated software, we are actually also building it with harder to manage group of people, simply because the amount of people crammed in one office is no longer enough for some types of projects. Okay, so that's the nice part of it. Take into account also the problem that the hard international competition means that we have to do best possible quality and have best possible productivity with the lowest possible costs. It's a really controversial situation. On the other hand, we have education. I mean, in Finland we have abundance of IT people. In India we have millions and millions of people with the background in computer science or information technology, something to do with programming. But still, the real professionals are far and few. For example, the companies developing motherboard systems, the component to which every other component in PC is connected, they needed a BIOS, basic input-output system developers, so that they could incorporate their new features of motherboards into their products. But the actual problem 10 years ago was that there was no people who were familiar enough with the BIOS systems so that they could develop them. So actually the largest problem in developing new motherboard systems was that there simply were no developers who were professional or experienced enough in BIOS systems so that these new additions could be incorporated. And that was global shortage of people. Okay, so on the other way around, since we have already long passed the point where one software developer could do everything on product themselves, we have to consider what is actually the work of software professional nowadays. Of course, it's teamwork. We have to have people communicating to each other. We have to have design and documentation, and there's simply too much work in each software product that we can do it simply with one person. On the other hand, it also means that communication and social skills against the stereotype are really important, and actually some things like social skills and knowledge of human nature are really important in managing software project. On the other hand, it also means that, for example, the UML notation we are talking about in this course is actually important part of software professionalism, simply because it's a way to convey knowledge from your head to other people, because they can see inside your head, or if they can, you should go to emergency room immediately. But it's important to be able to describe to your teammates what you are doing. That's also one part of this other part, that this course talks about planning and design, probably to a degree that you will be sick of it when this course is the course has ended. But it's actually really important, because technically we are building more and more complicated systems with more and more connections to different systems in more heterogeneous amount of platforms. We have also the organizational problems. We are dealing with people who lie and cheat and forget things, so that's also a problem. And planning-wise, we have to work with stakeholders, external organizations, and possibly have external offices and places where we can't simply walk to people and talk to them that way. So to cap this presentation on the basic idea what is software and what is software process, I'd like to point out a couple of things which are really important motivation for actually having this sort of course. This first part is not really any secret knowledge or anything. I mean, this stuff was published in 1987, so this is not really new information. But it's actually something that still has, influence on the software projects. These things still happen, even though this particular information was released almost 30 years ago. So the first point is that finding and fixing a software problem after delivery, releasing your game or giving your software to your customer is 100 times more expensive than finding and fixing the problem during the design and requirements phase. So cutting out design, cutting out testing during development, it's not just wise from the financial perspective, but still it keeps happening. The other point is that even if you have infinite resources, you only can tighten your schedule by 25%. So early releases and these sort of things are possible, but they are costly, and you have to have some sort of a game plan here. For each dollar used in project, companies will spend $2 in maintenance. This includes all types of projects, because even after you have released your game, you have to make patches for it, or add features, or do marketing, or release it on another platform. So all these sorts of things add up. So even if you have money to do the project, you still need money to maintain and support your product. Of course, the larger your product is, the more expensive it will get, and if you have large system, large project and large product, it will cost more. You can't create large project with small costs. You are cheating somewhere, or you are being optimistic about something. And also, going further, in software projects, the hardware doesn't cost anything. Most of the project costs go to software. And in 85, it was 85% software, 15% to hardware. Now it's probably something like 99.9% to software, and that 1 promille goes to hardware, and probably something like a USB sensor needed for some software system to function. Usually hardware costs are negligible compared to software. Also, if we are talking about large projects, it's not uncommon that the programming stuff, actually writing out the software, is only 15% of the total effort. Rest is verification, validation, testing, design, collecting requirements, reviewing your source code, administrative tasks, these sort of things. And the larger your project, the larger the amount of overhead on something else than programming. And of course, the review work, preparing and not doing testing and verification, means that you, at most, 60% of defects can be found without actually turning on the software and testing stuff out. So even if you are really meticulous with your development work, you still will find only something like 60% of your problems. You have to test your software at some point. The final point on this slide means that 80% of output comes from 20% of your programmers. It's actually not that people who do programming are lazy or bad or anything like that. It's just that the experience and the adaptability to your domain, or knowing what you are doing, is so important that people who are experienced in the domain and the programming language and the platform are really hugely more productive than people who are just learning things or are not familiar with the system we are developing for. Finally, this is the last slide on this presentation. This is Standish Group report on project outcomes. It's from year 2000, but it's still something that holds true today. The numbers haven't changed that much. It's alarming, actually. The successful projects are only 1/4 of all the software projects ever started. Actually, it's almost the amount of cancelled projects. The projects which were, for any reason, thought that this won't work, we have to cancel this. It's almost the same. And the rest of these projects are completed late, they go over budget, or they are missing features. And considering the late achievements of the National Railway Company, VR in Finland, or the Danske Bank net bank system 10 years ago, it's also real telltale number that you can't buy success. Even if you have money, you have resources, you may still fail. So that is the reason why we are talking about planning and features and actually have to think about how to build our software.